Okay, hi everyone. So, for a really long time, you've just been told that things like this are true. That this is like this. Oh, whoops. And, you never really knew why to believe this, and nobody really told you why. So now let's prove why. So it all comes from this. So what does this symbol even mean? Let's recall the symbols e to the x mean, by definition, this symbol means an infinite series, really a power series, x to the n over n factorial, n equals 0 to infinity. Okay, and so that's what we have to use to prove this. This captures things like 2 to the third times 2 to the fifth is, well, I guess I should put it over here since x plus y. Anyway, there's 8 of them. So 2 to the third is 2 times 2 times 2. 2 to the fifth is 2 times 2 times 2 times 2 times 2. And that is, in fact, 2 to the eighth. But this only works for integers. And so, in fact, it's true for any complex numbers. And so let's prove this now. Okay. So, first of all, e to the x plus y is by definition, it is an infinite sum of x plus y to the n over n factorial, where n is equals 0, 1, 2, 3, 4, infinite sum. Okay? And let's complete, e to the y by definition is y to the n over n factorial, n equals 0 to infinity. Okay. Now, let's agree that writing ... so something like 1 plus x squared over 2 plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus ... means, let's agree that writing that means the infinite sum x to the n over n factorial, n equals 0 to infinity, which means the limit of the partial sums. And let's agree to write this whenever the reader can see the pattern, and could come up with a general formula of every term forever and ever. Okay, so you can write this provided the reader could themselves come up with the general term. So if you have demonstrated the pattern adequately enough, then you're allowed to use ... Okay? Because this is just a symbol, and so let's just define it to be the limit of the partial sums, limit of the sequence of partial sums of the power series, just like we had before. Okay. So then, let's write this right-hand side out, okay? And we're going to check that it's equal to this. So, e to the x, e to the y equals, well, 1 plus x squared over 2 plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus ... times 1 plus y squared over 2 factorial plus y to the third over 3 factorial plus y to the fourth over 4 factorial plus ... Okay, now, expanding this product, first of all, let's give these, this product has 2 factors. Let's call the first factor capital A, and let's call the second factor capital B, okay? So, expanding this product will give a sum of terms, okay? And we have to understand the pattern in order to prove that it is in fact going to give this same thing, okay? So let's understand the pattern. First of all, remember, this we can expand by the binomial theorem, this general term. What's x plus y to the n? Well, it's going to be, by the binomial theorem, we're going to have something over n factorial. What is this? It's going to be x to the j y to the n minus j. And now we're going to take j equals 0 to n. So x plus y to the n will be this. Okay, and we'll see that very explicitly in a moment. So expanding this will give a sum of terms. Consider the terms of total degree 4. Why 4? Well, maybe actually 3 would be better. We just need to see what the pattern is. So of total degree 3, that means they could be x to the third, x squared y, xy squared, or y to the third. How many of these will appear? Well, let's see. So we could choose this term, and then it's going to hit every single term in the factor b when we multiply it out, but you'll see that the only way we can get a total degree, okay, I said total degree 3. Okay, so this term can only be total degree 3 if it hits the 1. In other words, we are going to get x to the third over 3 factorial from A. And then how else could we get a term of total degree 3? Well, this thing will hit there and be 4. Then it'll be degree 5. X to the fourth times y would be degree 5. X to the fourth times y squared would be degree 6. So you see that we're not going to get anything from this. From this one, we will get something. It'll hit this and be total degree 2. That's not what we want. But then it'll hit the y and be total degree 3. So we're going to get these two coming together and give us x squared y over 2. X squared y over 2 factorial. 2 is 2 factorial. Similarly, this x can only give total degree 3 when it hits a y squared, which comes along with a 2 factorial, right? So we'll get an x y squared over 2 factorial. And then here, this 1 can actually give us a total degree 3. It can when it hits this y to the third. And that will come along with the 3 factorial in the denominator. Okay, and now look at this. This is a sum from j equals 0 to 3 of x to the j, y to the 3 minus j. And now what? Now there's some sort of things down here. Well, what are they? Well, they are j factorial and 3 minus j factorial. Do you see that that is correct? Therefore, pause the video and make sure you see that this is correct. So when we expand the product of a times b, and we get terms of total degree n, then they will exactly be the sum of j equals 0 to n of x to the j over j factorial times y to the n minus j, just the rest of the degree j terms, times n minus j factorial. Okay? And that will work every time. So if we did total degree 4, you'll see this still works. Okay. So for example, the total degree 4, we'd have x squared and a y squared coming together. And you see we're going to get a 2 factorial and a 2 factorial, both of them at once. And so that's why we need both of these denominators. Anyway, so now, but that is exactly the same, is exactly matching the terms of total degree n in what? In the sum from n equals 0 to infinity of x plus y to the n over n factorial. Well, except for maybe an n factorial, but now I'm getting confused, so let me see. Let's see, so if we do this, we're going to get sum from n equals 0 to infinity. Now x plus y to the n will now be a sum from j equals 0 to n, x to the j over, oh I see, y to the, oh I see. We're going to get a n choose j from the binomial theorem. N choose j, x to the j, y to the n minus j. Okay, and then there's this n factorial down here. Now look, what is n choose j? Remember what n choose j is? N choose j is actually n factorial over j factorial times n minus j factorial. And so we can rewrite this sum, n equals 0 to infinity, of something over n factorial. But what is that thing? It's a sum, it's a finite sum, j equals 0 to n, of n factorial over j factorial, n minus j factorial, times x to the j, y to the n minus j, and cancel, and lo and behold, the xj and the j factorial, n minus j and the n minus j factorial is exactly what we get up here. Okay? So, is that it? That's it. So you see that we needed this n factorial here because it's going to cancel the n factorial that comes in the binomial theorem, giving exactly these ones, which are exactly what we get from cross-multiplying things. Okay? I don't know if this is called cross-multiply, but you're just multiplying and expanding. Okay. So that's it. That's all, folks. Yeah, you're supposed to do like that. Now you finally actually know why this is true. Wow. Absolutely wonderful. Okay, can you do this yourself? Take this, move it over here, blank sheet of paper, prove this for all x and y in the complex numbers. Okay? Keep going. Prove. Can you do it? Okay. You'll definitely need to know what n choose j is. N factorial over j factorial n minus j factorial. That was previously in our book. And these are exactly the terms in Pascal's triangle. That's what they are. You know, they're these things. Etc. X plus y to the fourth. Right. What is the 6? Well, it's 4, choose 2, which is 4 factorial over 2 factorial and 4 minus 2 factorial, which is 4 factorial over 2 factorial times 2 factorial, which is 4, 3, 2, 1 multiplied together, 2, 1 multiplied together, 2, 1 multiplied together. Let's cancel these. Let's cancel this. 2 times 3, that's a 6. So yeah, you really do, you do know what's going on here. The formulas might be a lot, but you know how to do x plus y to the fourth, right? X plus y times x plus y times x plus y times x plus y. You know, how many x squared, y squareds? Well, we could choose these two and these two, or we could choose this. Anyway, there's 6 ways to do it. And in general, x plus y to the n is a sum of these Pascal triangle things with powers marching up and down. This n factorial from the exponential definition will cancel and give exactly the xj over j factorial, yn minus j over n minus j factorial, which are exactly these sort of things. Okay? Super important. Can you do it yourself?